So good morning students. Today I have decided that I would be discussing on few aspects of statistical physics. Since you had given your exam yesterday, you have now the basic concepts of statistical physics set and strong. So right now, therefore, I think few conceptual understanding of why at all we are going through these concepts and how do we apply these concepts in real life in our study of physics. I want to discuss a little bit of that now today. For example, and this basically I would like to do for quantum statistics, because for classical statistics uh, it could have been done for classical statistics as well, but I am preferring to choose this applications of statistical physics for quantum statistics, because you have done quite a lot of quantum statistics now, so you will see, you will understand the applications quite well. So you see, if you remember the occupation index that we had therefore found out, the occupation index that we have learned in our study of statistical physics was Ni by Gi. Now what is Ni? Ni is actually the number of particles, isn't it, in the cell I, in the ith compartment, and Gi is the, now you will know it well, and Gi is the number of cells in the ith compartment. It's number of cells of equal size satisfying the condition of equal a priori probability in the ith compartment. So Ni by Gi we have observed for our Bose-Einstein distribution. If we consider Bose-Einstein distribution, we have seen that Ni by Gi is equal to 1 by e to the power ui by kt minus 1. Okay, now, well, if we try to find out this, being this we call the occupation index, and this, as you know, that for Maxwell-Boltzmann distribution Ni by Gi is much less than 1, because the number of cells available is huge. Okay, and it is nearly equal to 1 for Bose-Einstein and exactly equal to 1 for Fermi-Dirac statistics because of Pauli exclusion principle. So if we now try to find out the number of particles having frequency between nu and nu plus d nu, so suppose we consider a spherical concept. For the conceptual understanding, we consider a spherical shell like this. We consider over here the radius of the cell as nu and the extended radius over here as d nu. So number of particles between nu and nu plus d nu, that means within the spherical shell, we call this as n nu d nu. Okay, so n nu d nu will be equal to g nu d nu. Okay, so following the previous expression that we saw just now, Ni is equal to Gi by e to the power ui by kt. So n nu d nu is equal to g nu d nu divided by, now we have seen in Bose-Einstein distribution, photons obey Bose-Einstein statistics and the energy ui for photon is h nu. So e to the power h nu by kt minus 1. Okay, so this we can write for photons. Okay, that g nu d nu is equal to this. Now, so again I repeat that g nu d nu actually gives the number of cells in phase space volume lying between the energy interval nu and nu, h nu and h nu plus d nu. Okay, so number of cells lying within the energy interval h nu and h nu plus d nu. So if you just consider this itself as the energy interval and you multiply this by h and this as h nu d nu, okay, h nu plus d nu, okay, this portion and this portion, then g nu d nu is the number of cells within this. Okay, so the corresponding values for momentum, as you know, if you try to do it in terms of momentum, because when you consider a phase space, it is a space of position and momentum. So P, the momentum, is equal to h nu by c, okay, and well, dp therefore will be equal to h by c d nu, okay. So you see, well, the number of cells in the phase space in the momentum between p and p plus dp, because you see dp is correlated to d nu. So if you consider the same spherical shell like this, okay, with momentum lying between p and this is dp, so between p and p plus dp, okay. So the number of cells in the phase space, so this is again a phase space in the momentum interval p and p plus dp, is therefore now gp dp. The number of cells in space having frequency between nu and nu plus d nu is g nu d nu. Between nu and nu plus d nu, it is g nu d nu. And the number of cells having momentum between p and p plus dp, number of cells, will be gp dp, isn't it? Now how do you find this number? It is actually equal to the volume of this cell divided by the volume of a single cell. The volume of a single cell, okay, the volume of a single cell in quantum mechanics, what is it equal to? It's limited by Heisenberg's uncertainty principle. All of you know it is equal to h cube. And what is the volume of this spherical shell? The volume of this spherical shell will be what? 4 pi p square dp, okay, into v. All right. So how do you find out the area? Area is circumference into thickness. So 4 pi p square dp, and if v that is for your area is 4 pi p square times the thickness dp is the volume. So the volume of the spherical shell is 4 pi p square dp, volume in momentum space, times v, the volume in position space. So it is the product of the two volume, dx dy dz, dpx dpy dpz. If you remember, that is the volume of the phase space. And the volume of a single cell limited by Heisenberg's uncertainty principle is h cube. So actually the volume of the spherical shell is this 4 pi p square dp by v. So the number of cells, okay, gp dp lying between momentum p and p plus dp is equal to 4 pi p square dp v by volume of a single cell. This conceptual understanding is very, very important, and this is what we use for Maxwell-Boltzmann, Bose-Einstein and Fermi-Dirac statistics. Now photons, they have two kinds of polarization, one clockwise and one for two kinds of polarization. For clockwise and anti-clockwise, polarization of photons, this number will be doubled. Okay, so for both kinds of photons, so for both kinds of photons, GP dP is equal to 8 pi p square dP V by H cube. Okay, so well, if we try to find out the value of n nu d nu, what is n nu d nu? The number of particles having momentum between nu, having frequency between nu and nu plus d nu, isn't it? That is n nu d nu. It is equal to g nu d nu divided by e to the power h nu by kt minus 1, isn't it? So see, you can write therefore n nu d nu is equal to g nu d nu divided by e to the power h nu by kt minus 1. Okay, so now if you write d nu in terms of nu, then you have to write your momentum p as h nu by c. Okay, for your g nu d nu, therefore you have to convert. See, we have done that before. You have to write your dp in terms of nu. That we have written before. If you see, it is there already. See, it is here. P is equal to h nu by c. So put h nu by c for p, and for dp you put h by c d nu. If you make that substitution, you will get your g nu d nu. Okay, so what is your g nu d nu? Your g nu d nu will be equal to 8 pi v by c cube nu square d nu divided by e to the power h nu by kt minus 1. This basically in terms of nu is your Planck's radiation law, and if you convert this to wavelength, you will get the corresponding value for wavelength. Okay, if you really change your since you have your number n nu d nu, and since each photon has energy h nu, the energy density E nu d nu, how will you define the energy? Because this actually is correlated. This is correlated to Planck's radiation law. This is correlated to Planck's radiation law. Okay, now how it is correlated, let us find out. Okay, and finish off. All right, so you see, well, you can therefore say that each photon has energy in h nu. Each photon, because in Planck's radiation law we talk about the energy, isn't it? And that is n nu d nu, which is the number. Now each photon has energy h nu. So if you try to find out the energy density, which is Planck's radiation law, what does energy density tell you? Energy density is E nu d nu. Okay, that is your energy density. How do you define your energy density? It is defined as the amount of energy per unit volume lying between frequencies nu and nu plus d nu. So basically E nu d nu is h nu, this is energy of one photon, times the number of photons between frequency nu and nu plus d nu per unit volume. Okay, so if this is what you have for your energy density, then you can show that this, if you just substitute the expression, you will see it is equal to 8 pi h nu cube d nu by c cube 1 by e to the power h nu by kt minus 1. This is Planck's radiation law. This is Planck's radiation law. Okay, in terms of frequency. If you convert this to wavelength, okay, then you have to put nu as, to convert to wavelength, put nu as equal to c by lambda and do your conversion. So d nu will be equal to minus c by lambda square d lambda. So when you make the substitution, you can neglect the negative sign. Okay, in that case then you can show that your E lambda d lambda, okay, in terms of lambda, E lambda d lambda is equal to 8 pi hc by lambda to the power of 5 d lambda e to the power hc by lambda kt minus 1. The same expression that you did for Planck's radiation law. So this we obtain absolutely from the concept of statistical physics, the Planck's radiation law. And you can also obtain the Stefan-Boltzmann law and the Wien's displacement law also from here. This is Planck's radiation law, and one can obtain Wien's displacement law and Stefan-Boltzmann law. From the same expression. Okay, alright, so let's stop over here now.